Hello, everyone, and thank you for joining us today. My name is Erin Majerowitz, and I will be your host for this NASA Technology Transfer Program webinar on NASA Goddard's concept for advanced spaceborne synthetic aperture radar. It is my pleasure to introduce our presenter for today, Dr. John Ranson. Dr. John Ranson is a senior scientist with the Biospheric Sciences Laboratory at NASA's Goddard Space Flight Center. He received a BS in Watershed Sciences and an MS in Earth Resources from Colorado State University, where his graduate research involved geologic and forest covering mapping. He later joined the Laboratory for Applications of Remote Sensing, otherwise known as LARS, at Purdue University, where he earned his PhD. His doctoral research quantified bidirectional reflectance characteristics of agricultural crops. In 1986, Dr. Ranson joined the Biospheric Sciences branch, where he has developed remote sensing linkages to forest ecosystem models, conducted optical and radar research while leading several domestic and international projects for NASA. He has also served as the Deputy Project Scientist and Project Scientist of the EOS Terra mission. He was also the lead on the Destiny LiDAR concept. His current research is focused on active and passive remote sensing of ecosystem dynamics of the boreal forest, especially in Siberia. He has served as the chief of the Biospheric Science Laboratory from 2003 to 2014, and twice served as an acting headquarters program manager. He has authored and co-authored over 100 peer-reviewed journal articles and has been awarded a NASA Leadership Medal, Goddard Exceptional Supervisor Award, and numerous Goddard Performance Awards. Dr. John Ranson is also an adjunct faculty member for Johns Hopkins University. Immediately following Dr. Ranson's presentation on the advanced spaceborne synthetic aperture radar technology, Goddard's marketing manager, Samantha Kilgore, will be providing an overview on how to license technology with NASA. Now, before we get started, I'd like to point out that your microphones will be muted throughout this presentation. If you have any questions, please type them into the chat box and we will respond to your questions via email at a later date. So at this point, I'm going to turn it over to you, Dr. Ranson.
Okay, so we'll get started here. My name is John Ranson, and I'll be talking through these slides for you today, and looking forward to a good discussion about this new spaceborne SAR concept. Present are the members, three members of the invention team. Rafael Rincon, the lead electrical engineer and SAR technologist, and Lola Patimbo, a biospheric research scientist at NASA Goddard. And of course, Rafael's also with NASA Goddard. And then there's myself giving you this presentation. I'm also in the Biospheric Sciences branch at Goddard. And then we have a fourth person, Lynn Carter, who was at Goddard, but is now at the University of Arizona. So that's who we are, and together we put together the ideas, concepts, and the actual material invention that we're talking about today. So we started out to improve SAR remote sensing by reducing the size, weight, and power of lower frequency radars, and came up with the concept of a so-called smart panel approach using direct beamforming technology as our SAR evolved from a single panel system to an airborne dual panel P-band system that's also interferometric, and to a P-band space qualified system within number of panels, if you wish. And so we have flown these and we've tested them and on aircraft and of course in test chambers and so forth. These are just pictures of the various types of radars that we have ranging from the first one, an L-band system that we flew on P3, a DVSAR-2, which shows that the first smart panel concept, a diagram of EcoSAR, which is a dual antenna P-band system, so it can do interferometry real time, and it also is extremely versatile in how it acquires data, and we'll show more about that as we go. And then working on systems now that are intended to go to space, primarily to the moon and Mars. So the story behind this technology, as I mentioned, is based on a smart panel, which combines modular, low power, and lightweight design approach with innovative techniques. So the design, as it is compact, does require less power, and is lightweight, made of composite materials. So it has a multi-channel software-defined waveforms, digital beamforming, and reconfigurable hardware, and it's all on the same panel. So the antenna and the electronics for beamforming are on the panel, and they are reconfigurable on the fly. And it enables meter class resolution measurements of global surfaces as well as subsurface if you use the longer wavelength bands that are available here. So overall, the mass power and development cost of space SARs are reduced using this concept. And in addition to the flexibility in terms of the measurement acquisitions, that of course provides scientists with the means to tailor measurements for the various research and applications that they want to do. So the smart panel is illustrated here in this center panel. So you can just see that this is all on one panel, and it's got all the antenna and all the electronics and the controlling and housekeeping software, as well as the data ports which go to the to storage on the spacecraft itself. So the idea is that you can fly this panel, and if you look over here on the right, you see a spacecraft actually it's over Mars and the Moon at the same time, but it's just for illustration, of course. And the idea is that this thing can take multi-beam measurements. You can point multiple beams and acquire that data simultaneously. And also, if you're flying P-band, for example, it not only maps the surface, but it can penetrate the subsurface and find ice lenses or structures of subterranean features on planets, so and also on the Earth. It's also really good for Earth sensing. As you see down below, there's just an example of a wetland, and with a P-band, and it shows a lot of detail of the structure of this wetland area without going into too much detail. But it's really useful for understanding how much trees are growing there, whether the water is standing beneath the trees, and so forth. So you can get a picture of the hydrology as well as the ecology using this type of technology. So the waveforms the radar waveforms are software defined, and the radar beam can be steered with no phase shifters and no moving parts. And the transmit beam pattern is also controllable. So it enables imaging both sides of the track, and as well as nadir, selectable incidence angles, selectable range resolution, and an increase in the measurement swath area without degrading the measurement resolution. So an example of that is this upper figure where you have the panel moving along over a surface, and here we have the radar configured to look left and look right. So multiple beams and acquiring essentially double the swath that you would get from a typical single direction radar system. And what's really interesting about this is that we can reconfigure the beam pattern to put the energy where we want it. So this figure down below shows essentially the beam pattern. The yellow is the conventional SAR, so one look angle off to the side, and there's a lot of noise near that beam. Whereas this approach enables the energy to be put into two beam regions and suppress the noise elsewhere where we're not using it. We can actually push that noise outside of the areas that we're actually measuring. So it definitely improves the radar illumination. So we have flown this, as I've mentioned, and these are examples of the different modes that have been tested with actual data shown below those. So here's the just reproducing a typical side-looking SAR and the image that came with that. And then here it's looking at the two beams simultaneously as we're flying along. So you get these two strips at the same time. And here is a case where we're using a single antenna and actually doing single pass INSAR. Now, in that particular case, the beam separation is fairly small, so we can't measure very tall things. But when we put it into a situation where we can look at the same area from a wider or a longer baseline, then we can, of course, see more features on the Earth. I'll show you an example of how we did that with an aircraft. We can do scatterometry by changing the illumination angle any way we want. And then we can even do nadir altimetry with that. And then, so these have all been tested and shown, and they work. So this gives us the opportunity to tailor the radar to the mission needs. So it's not necessary to tailor the mission to what the radar can do so much anymore. We can configure these panels to meet specific measurement requirements. So this enables modular multi-panel approach that then allows the customization of the instrument architecture for specific flight missions. So missions to Earth, Moon, or Mars, what we have in mind right now. These panels then can be configured around a spacecraft bus. The example I have in the middle panel shows actually the way 6 panels would be configured on the spacecraft bus. They're essentially wrapped around. So there's 2 here on the right, 2 in the back, and 2 on the left to comprise these 6 panels. And then they're deployed in space to provide this very large panel. And then, of course, there would also be a solar array up here. But it's a much smaller antenna surface than which is currently being used. And of course, has all this flexibility as well. So our applications we've done so far are the Earth ones. So we've looked at forests and wetlands, and to get a feel for how this technology works for forest ecosystem mapping, something that NASA is very interested in. But the next journey for this is to the Moon and Mars to start looking at subsurface features. So here's some examples. The subsurface topography that we're seeing in the bottom panel is, of course, a an earthbound image. It's actually ice covered, as we see in the Landsat image that goes with that area. But you can penetrate that ice and actually see the subsurface features. It's also quite possible to locate ice and water and regions perhaps hospitable to life below the surface, like at Mars. So at Mars, so far we know we can scrape a little bit of the soil off and see ice. With this technology, we can go several meters into the subsurface to see what's there. So commercially, of course, there are all the applications that people want to use for SAR, whether it's for agriculture or forestry or urban studies or looking for subsurface features. Those can all be done with this, and they can be reconfigured for different applications as necessary. So that's a real value, I believe, in this technology. And then finally, where we're going is trying to launch these longer wavelength SARs for planetary exploration. And so we have quite a bit of activity at Goddard to push this out into space. So I think that's all I have.
Great. Thank you so much. That's all the time we have for questions today. If we didn't get to your question during the Q&A session, then we will follow up with you via email within the next week. If you have additional questions, then please feel free to submit them to the email address at the bottom of the screen, and we'll be sure to follow up with answers to those as well. Once again, we truly appreciate you guys for taking the time to be with us today. And thank you very much to Dr. Ranson for his presentation, along with Samantha Kilgore and Raphael for your answers to all of the questions during the Q&A.